So I am glad to be here. I know many of you, others I don't. I work closely with Aspire in the university in the USU Technology Transfer Office. And the genesis of this tech talk was just to make sure that the Aspire's innovation partners and all those that are associated with Aspire understand exactly what we're doing with regard to technology transfer from the university partners. We've got the core university partners, the five that are developing technologies in association with our innovation partners. And so I'm just going to give you a little bit of background as to how exactly this all works and some of the things that Aspire is attempting to do as an engineering research center. So I'm going to share my screen here. So technology transfer in Aspire or any ERC, and it all started with these guys. And for those of you who might be fans of musical theater, you'll notice Lin-Manuel Miranda. It didn't start with him, but it did start with a man he portrayed in Hamilton, Alexander Hamilton. And that's Daveed Diggs on the right, and he portrayed Thomas Jefferson. They weren't exactly going for similar looks, but they did a great job. Hamilton, you might remember, advocated a strong central federal government where things were much more centralized than the Jeffersonian model, which advocated taking it and putting it out to individuals, saying that individuals in the marketplace of ideas were the best ones to develop technologies and businesses, whereas Hamilton was much more centralized. So pre-1980, with regard to innovations that universities came up with, it was very much the Hamiltonian approach. Any innovations that universities came up with that were funded in whole or in part by federal dollars, grants from the NSF or the NIH or whoever it might be, the government owned those inventions. Universities couldn't do anything with them. It resulted in a whole bunch of inventions that never went anywhere, didn't do anything. And then by 1980, the government had a grand total of 28,000 patents over the course of its entire history, including all of the patents that it had, that universities had created with federal funding. And less than 5% of those had even been attempted to be commercialized. And yearly, the grand total of all the American universities, they got 300 patents a year. And you can imagine why this is so, because universities weren't really motivated to get patents because they didn't own them and they couldn't do anything with them. A few government agencies saw the problem here, and they said, we need more of a Jeffersonian approach where the universities are taking out the inventions that they're inventing and try to commercialize them instead of just put them into the central government database and have them sit there. So a few government agencies started assigning to institutions, but not all. And one of those that did not was the Department of Energy, and Purdue, one of our academic partners at Aspire. The researchers there had had enough. They had come up with some really great innovations with these DOE grants. They didn't own them, they couldn't do anything with them. And so they complained to their senator, whose name was Birch Bayh. And Birch Bayh and Bob Dole came up with the Bayh-Dole Act, which was much more, again, of a Jeffersonian approach, which gave the institutions ownership of the inventions, even if they had used federal dollars to develop them. That quickly, with universities now being able to profit from their inventions, 300 patents per year went up an order of magnitude, 3,000 per year. And that was in 2010, and now it's many more. with several billion in commercialization revenue. Several big universities like Stanford had some medical innovations, in Columbia and University of Minnesota and MIT and some others. But the one thing that everybody uses as an example of this paradigm shift is the Gatorade. University of Florida came up with this interesting, their athletic teams were complaining about being thirsty during hot practices, this being Florida, and water just wasn't doing it for them. And so university researchers came up with a formula for a sports drink that had great success with their athletic teams. And they thought, we want to patent this and take it out. And that became Gatorade. In fact, that's why the name, and they, of course, have gotten quite a bit of money from that. So several years after this was going on, Regan Zane came to USU and thought, I want to create an engineering research center. And so he proposed one, Select, and most of you know this history. That was rejected, but he went ahead and created the Select Center anyway. And from Select came Aspire, the engineering research center that we're a part of here. Aspire fully embraces a new paradigm of user-inspired and translational research. Universities traditionally have been foundational research. A professor goes and he researches whatever he wants to in his field. If it looks interesting to him, he starts poking around, looks into it, writes a paper, moves on. Doesn't really have an impact on society. What Bayh-Dole did, and what the direction of universities is very much, is user-inspired translational research. And of course, Aspire is very much in that paradigm. So we got Dave, I'm spacing Dave's last name, Christensen, as the innovation director, getting all you guys, the innovation partners, involved in what Aspire was doing. An extremely important part to make sure that Aspire is working on things that companies actually care about. Dave was eventually replaced by Don, and the technology commercialization offices of the different universities are involved to the extent that Aspire and the industry partner work together to create a new innovation, and the university technology transfer offices work to get those innovations out, generally through licenses. Licensing to, for example, the company that was partnering with Aspire researchers, giving it money to do so, or other entities. Obviously, the industry partners of Aspire are the favored members, and they're the ones that we want to get these technologies out to first, because very often they've been involved in the research that created the innovation in the first place, and because you're members. So one thing that we're doing in trying to help this along, helping this get these technologies out, it's obviously a very interesting field in electrification of transportation, a very new one. And so, as you well know, we're still trying to figure things out as we go along. And one of the things that we are starting to do now is contacting the the industry partners of Aspire and asking them questions of what are your pain points? What are you looking for? How can we help? Not only to see where a match is with existing technologies in the university's portfolios, but also what directions the research should be taking. And obviously there's a lot of that going on in Aspire already. This is an additional effort by our technology transfer office. So I'm going to throw it over to Vicki Ballard for just a minute. She's the one that's spearheading this effort, and she's going to briefly describe what she's all about here.
Oh, thanks so much, Alan. First off, I'm so excited to meet all of you. I've heard so much about you from Alan and from Don. My name's Vicki Ballard, and Alan and Don asked me to take on a project. So I am known as a commercialization analyst, and it's my hope to connect with the different Aspire members and potential stakeholders and identifying, like Alan said, pain points or needs that will help us as we inform technology-based solutions. So simply put, I would like to more closely link our Aspire technology development with your needs as members and as contributors to this amazing organization. So yeah, I will be working and calling, emailing. Hopefully you guys will be willing to speak with me as I learn from each of you and as I help put together some of our directions and also ensure that you have access to all the amazing technologies that Aspire offers.
Thank you, Vicki. So I thought you might be, just to close out my portion of the presentation, thought you might be interested in a general overview of the portfolio of technologies within the Aspire area. This is primarily USU technologies. It doesn't include those technologies from Purdue and Colorado State and University of Auckland and UTEP. But they're similar in their makeup. So what we've got is these are technologies that are currently available and that we're working on currently getting out there in a commercialization sense. These do not include those that have already been exclusively licensed or are otherwise done available. So you can see that the two biggest areas are the wireless power transfer area and the power conversion systems. Then we have a few others and energy storage systems. That said, so I'm going to throw it over to Durai, and Durai and Steve are going to give you a little bit more detail on some of the technologies in this portfolio. So Durai, take it away.
Thanks, Alan. Don, thanks for the introduction. Let me just share the screen. So, I was asked by Don to present highlight one of the IP that I contributed as a student at USU. So I chose a topic which is pretty easy to follow. Maybe not the coolest IP from USU, but one which is quite easy to follow for me to explain. So it's centered around power converter for battery management system. And for this particular IP, there were, other than me and Regan, there were quite a number of folks involved. So I just wanted to mention that it's a collaborative effort. And some of the results I will share. The IP is quick, like an idea, but the staff and engineers at USU are the ones who took this IP to build some technology demonstrators. So I'll today introduce about a power converter topology IP. And before I do that, I'll first give a brief background to the application itself. So the application here is active cell balancing. Why do you need active cell balancing in large battery packs? And then highlight one example lab prototype that's actually built at USU to help you visualize what a system looks like. And then I'll discuss about the fine details about the IP I will highlight today. And then briefly show a low power technology demonstrator, and then how it translated to do a DOE project where like a full system was demonstrated by the team at USU. And then at the end, if there is time, we could have a Q&A session. So quickly introducing the topic of why we need cell balancing. Like as maybe many folks are aware that in a battery pack, there are multiple battery cells usually connected in series and to reach a desired high voltage, and then in parallel to reach a desired power level. And then due to tolerances, there is always a mismatch between two cells. So to ensure safe operation of the battery pack, there is always a central uh, management system, which is monitoring all the cell voltages individually and trying to ensure safe operation with an objective of either trying to maintain equal state of charge or state of health, whatever is the objective, but there is a central BMS that has to be there to ensure the safe operation. And at USU, there is lots of work has been done with collaboration of other universities around the state of health battery management algorithms. But to implement the algorithms, you need power electronics to do that. So for example, when you have a battery pack, usually it's accompanied by a power converter. It can be an AC-DC converter or a DC-DC converter. That's kind of post-processing the power from the battery so that it can match with the desired load requirements, like maybe regulating the voltage or the current or stepping up the voltage or providing galvanic isolation. There might be multiple objectives this power converter might be doing, but the key item here is that there is usually a power converter accompanied with a battery pack. And you could so the idea is at USU is you could always combine the power conversion stage with the battery balancing circuits and come up with an architecture that is referred to as active cell balancing. So that means there is a power converter for every cell, so that you can individually regulate power from that cell. So it essentially means there is one DC-DC converter per cell or for a particular set of cells. So that allows you to regulate the current from each battery cell in a battery pack. So now we are able to implement some of the active balancing algorithms. And this is quite beneficial when you're at high, when the battery pack is typically a high power battery pack. And to the example here, to the right side, you're seeing an example of a battery pack with the active cell balancing converters on the top. And then the cells you can see are on the bottom side. This was done long back at USU, like 2016. So definitely this has multiple advantages of implementing some advanced algorithms, but then you need power electronics that can add to the cost here with so many auxiliary components. As you see, there's lots of transformers for galvanic isolation and so on. So with that, there was an opportunity while I was a student there to reduce the cost of implementation of these power converters. So one idea that was eventually patented was to look into how to reduce the cost. For example, I'll take a minute to highlight. So when you have a DC-DC converter, so there is usually a primary side semiconductor and then a transformer for galvanic isolation. It need not be in all applications, but for most grid connected applications, or whenever you're connecting to a high voltage DC bus or an AC bus, you want galvanic isolation for safety. And then you will have a secondary side power electronics. So each cell will have a primary side power electronics and the secondary side power electronics and a galvanic isolation. So one idea was to say that, okay, how can we reduce the number of passive components? So that's where the idea of a multi-port converter came in. And essentially, since we are interested in regulating just the battery current of each cell, we don't really need a dedicated secondary bridge for all the cells. So we can have a central unit for a secondary bridge and a central winding. This way you can achieve the galvanic isolation required just through one winding. So you are still able to regulate individual currents of each cell, but reduce the number of semiconductors used. So that's the core idea here. And as I was saying, the main advantages would be reduced component count. Earlier, if let's say you had three battery cells, you would essentially need a total of six MOSFET bridges, 3 for the primary and 3 for the secondary. But in this particular architecture, you will only see 4 bridges because the secondary, there is only one secondary and 3 primary bridges. And since there's one magnetic structure, it also helps to meet the creepage and clearance requirement for the safety requirements. And the topology and the control later, which will be shown, is such a way that it's easy to scale. It's not just 3 ports. You can scale up to 10 ports, 20 ports without introducing control complexity. That's the main differentiator in the power technology here compared to some of the existing. So just to help visualize, I quickly put this together from a really old material I had. So the idea here is you will have a common secondary winding and individual primary windings where each of this primary winding is connecting to a battery cell, but there is a common secondary winding that would be connected, eventually go to the load side, since we only have one load. So in a battery management system, if you remember the early battery pack I've shown with all the power converters on top, all those are pretty much in close proximity. So that means you could have a secondary winding that goes all along through because the transformers, individual transformers are very close to each other. So you don't really introduce extra copper losses due to that. But then you could, since you only have one secondary, you could just completely insulate this secondary winding to meet your high voltage requirements. So need not necessarily that you have to understand all the fine details, but I hope I conveyed the message there. And this was an IP that was filed in 2019. And thanks for the support from Alan and Regan. And this was surprisingly quickly issued as well in 2020. But I introduced the concept about this multi-port structure, but the IP was based around taking some of those ideas and mixing up with the battery management the active cell balancing requirements. So that uniquely led to this invention disclosure. For example, I'm just trying to show in the IP what we in the IP application, what we showed was a 20-cell battery balancing demonstrator. So you can have a 21-port converter. So you have 20 input ports and one output port, one central output port. So each cell would have its own semiconductors with a high frequency link port that can be all connected in series. Just some visualizations to show you can use any magnetic structure to do this. If it's an E-core structure, you will have the secondary go across through the center structure. It can also be a U-core or a toroid. Multiple embodiments are possible. But now it's just the concept of the hardware. Like you're now able to reduce the cost, but then how are you able to control the individual currents from the battery cells individually, so you're able to do some active balancing. So how is it achieved is each bridge here can generate a pulse width modulation whose width can be controlled. So that is an individual degree of control for each of the H bridges. And on the secondary side, you have a second active bridge where you can control its own pulse width and also the relative phase shift between all these bridges from primary to secondary. So there is enough degree of freedom for you to actively regulate battery currents of each of this cell. So there is quite a lot of equations here, but I just want to highlight that each battery port or each battery cell current can be regulated by the duty cycle alpha 1, alpha 2, alpha 3 individually. So you have an individual degree of control with very less coupling with the structure. And if you go through some of the math and understand that it's fairly easy system to decouple and put a closed loop around it. And to quickly show some waveforms here. So we have the primary bridges V1, V2, V3. So you can see the pulse widths are different, with V1, the primary bridge voltage being the lowest pulse width. Sorry, the primary bridge 2 being the lowest pulse width, and bridge 1 being the highest pulse width. And then you can control the phase shift between these bridges. So when I say the pulse widths here control the active current sharing from the bridges. So as I was just showing, the bridge 3 has the highest pulse width, though that means that will have the highest current drawn, whereas the bridge with the lowest pulse width will have the lowest current drawn. So that way you have this individual degree of freedom. And then there were some modulation techniques we used to ensure efficient switching of the devices to optimize the losses in the converter. But essentially, this is just showing that with this structure, you can individually regulate the currents independently by changing the pulse width here. So that way you're able to implement some of the BMS algorithms with this battery power converter topology. And with that, you can put a closed loop control with analyzing the small signal model, but the idea is you will have a battery management system that is giving you a reference, that your references are received for the output current and the individual cell currents that are required. And then the individual cell currents references will be regulated by the power converter closed loop, where the differential currents will be introduced by the duty cycle, and then the total power will be regulated by the phase shift. At the end, a quick simulation example here. This is the output current that's going to the load, and till this time frame here, we are drawing equal currents from all the 3 cells. And after this scenario, after this time instant, what happens is a command is received from the BMS saying that a difference in the battery currents is desired. And then, as you can see, from that point, slowly the converter is able to regulate a different level of battery currents. From here, for example, from 2.5 milliseconds to so on, the duty cycles change to regulate the battery currents as desired. And then there was a quick low power hardware demonstrator that was done. Before we could file the IP, we had to demonstrate that this works. As I was saying, so this is for a 3 battery cell with a common secondary, and we had a common secondary winding go through just a 100-watt quick small scale prototype demonstrator, proving the concept before we go file for the IP. And repeating the same thing, like when just the hardware results, like when you have the same duty cycle in all the 3 phases, you have the same currents from all the 3 battery cells. But the moment when you change the duty cycles, in this next slide here, you can introduce the asymmetry in the currents to start doing the active balancing. So based on this, later there was a DOE project proposal written where the concept of this was taken to demonstrate at a much higher power level, where the idea is to demonstrate a battery cycling facility where you can take the second used battery cells from battery electric vehicles from different vendors, different manufacturers, put them to this battery cyclers, provide some ancillary grid support. So that was the concept for this project. But then the whole idea is to just check this IP was implementable. So This was a small part of this big project where the DC-DC converters here were built using the multi-port IP that was just discussed. And then in that, like a 2 kilowatt prototype was built, a modular 2 kilowatt prototype was built, which can interface to a battery pack. So each of this 2 kilowatt prototype has up to 5 ports with 4 battery ports and 1 load port. And for this particular demonstration, battery modules from a used Nissan Leaf were used to show the system. As you can see, the power converter with the BMS inside is connected to this battery pack, which is quite modular, easy plug and play solution. And then that was one module. As I was saying, this is a much bigger system. So you have multiple modules as such that can be stacked in series and parallel to reach the power levels, because this is all galvanically isolated. So you can see this multiple power converters with their individual battery balancing algorithms running, connecting to their individual Nissan Leaf battery packs. So this technology could be demonstrated at a much higher level, of course, with implementing some advanced algorithms along with the power converter topology I just discussed. With that, I hope I was within time. Maybe if there are any questions I could answer. I know I have just breezed through all the slides there. So if there is any questions, I can take, I guess, Don.
Hi, Connor. I'm sorry. Hi, Durai. There's one question in the chat says, how did you figure out what you researched and designed was patentable? When did you decide you were able to patent it?
Okay, so the structure there itself, like just identifying the challenges, right? Like what's unique to the BMS itself. We could see that the multiple transformers lying very next to each other, and then there was always this requirement for reduced cost and also for requirement for the galvanic isolation for safety requirements. Then we were looking at strategies to do that, and we did not come across something that that potential, like there was no technology that could be readily used. So we had to come up with a new solution. We did some IP search really quick. Internally, that's always a part of, as a PhD student, you also do some literature review with having lots of background in that area. So that's when we felt that, okay, there is a significant improvement that we could gain. So that they gave me the confidence to reach out to Alan to discuss potential IP.
I might add here that Durai and Regan and the other researchers in the Aspire Center have a pretty good handle on what's new and interesting versus what's already been done, or as important, what's new and not very interesting. Universities traditionally have the traditional model of university researchers have been they sit at their desk and they think great thoughts and they come up with solutions that are looking for problems. Here, these guys turned it around, and a quick note on the patent. Those of you who are familiar with the patenting process know that it's long and drawn out. And the patent office always comes back with a rejection, always. And you have to go back and forth with the patent office, negotiating the scope of the claims and fighting about the prior art. And out of all of USU's portfolio of patents in all our different areas, the Aspire patents are by far the ones that go through the quickest. And I imagine that you've experienced that in your own patenting process with regard to this area, because so much of this is new that the patent office doesn't have a whole lot of prior art to compare it against, and they tend to go through rather quickly.
Yeah. So yeah, definitely lots of background within the lab, and also for the students here, mostly PhD students with lots of experience.
Durai, this is Kent Warner with John Deere. Thanks for the presentation. Real quick, a couple of technical things. Can this topology handle different voltages on the cells? I see you had 4 volts across the board, but if they're imbalanced, one might be off. And question number 2 is, can you push current the other way?
Oh yes, so maybe great question. So this is bidirectional, by the way. So we have active switches on both sides, so it can charge and discharge. So you can actively balance the current while charging or discharging. And typically you would ideally want the cells to be more or less equal voltages. So that makes them all symmetrical. When you're designing the power electronics, you would essentially design it symmetrically. But if you have a particular application where you want asymmetry inherently, you could definitely do that. And there is a region over which even with symmetry, you can handle a difference in voltages. But if there is a large difference in voltages from cell to cell, it might negatively affect the efficiency of this topology, but definitely handleable.
Yeah, makes sense. Thanks. Yeah, certainly you'd want them to be close, but my point was they're not identical. So
Right. So definitely like few volts is not a problem. And also when you're doing cell balance, you're not trying to drastically change the currents as well. You're just trying to introduce a small differential current, like, so that you actively balance it. Like, so this is quite easy to implement with this hardware.
okay, thank you.
Are there any other questions? If not, what we'll do is I've aligned here with Dr. Steve. We don't have a lot of time for his full presentation, so he's gonna do a teaser, and we'll come back, and at another time we'll be able to present more of his solutions. So I'll hand it over to Dr. Steve.
Well, thank you, Don. Thank you, everybody, for your time. I'm gonna, hopefully you can see my presentation now, and I'll keep it brief. I know that people are on tight schedules. This represents work that's been ongoing within Aspire and also INDOT and IP related to that. I'll give a little bit of a history, and some of you have seen this at prior Aspire meetings, and it actually, the initiation of this effort predated Aspire. It was with Select. It was Nadia Gritza had established or led a proposal to INDOT to explore the feasibility of dynamic wireless power transfer on Indiana roadways. And as time has continued on, of course, many things have occurred since that initiation. Big questions that were part of that are, what's the power levels that you would want to explore there or instantiate in a roadway? And then the second thing is it technically feasible? And one of the conclusions that have really come out of Aspire is, at least in Indiana, and it's consistent across a couple of different states that other teams have explored. Project 3 has really identified that for financial feasibility, you really have to consider instantiating dynamic wireless power transfer for heavy duty vehicles. You can, of course, utilize that for the lighter duty, but you have to build your system for heavy duty. And that's actually, we now are initiating a pilot in Indiana in a 1/4 mile section to do this. The power levels that are transferred from the roadway to the vehicle can be on the order of 200 kilowatts. when you think about that, those that aren't electrical engineers, in your home, an average home is drawing about 2 kilowatts. And so you're providing power to a vehicle, a fully loaded vehicle, on the order of 100 homes. And so that's a large amount of power. You can envision that the electrical coils that make this up are relatively large to get to that. And one of the technologies we've been exploring is 3-phase. And there you see it on this screen, it's 3-phase coils. In general, in electrical engineering, when you're providing power to large amounts of power, that is typically done in 3-phase. Okay, so I'll skip through here and say the tradition in dynamic wireless power transfer, most prior to Aspire, not all, but many have done single-phase designs. And I'll just highlight on the left-hand side, this is a single-phase system, and you know it's single-phase because on the transmitter side, the variable that you have is A, and then the receiver, A, little a. Each one on the transmitter and receiver has a single phase. And on the right-hand side, it shows kind of the issue associated with single phase. Your goal is to create the red line. And a single phase system on average will create that red line, but in practice at every instant, it's the blue line. This is the power being transferred across the roadway and onto the vehicle side. It's actually the power. This plot is the power at the DC bus of the vehicle. And you can see there's very large oscillations in that. And so you have to deal with that typically. On the AC source side, the utility, they would see something, they would see oscillations as well, large oscillations, and that's problematic. It's costly to deal with that. And so you would like to get rid of that by going to multi-phase like 3. Ideally, if you have an ideal system, on the left here is that single phase. On the right would be an instantiation if you did 3-phase. And just a quick line, the red line versus the blue, you can see the oscillations are greatly reduced. The problem with doing that is that in a coil system like these planar coils that are arranged like this, it's hard to make them ideal. There's an imbalance between phases. Here we have A, B, and C. Those are phases. And the imbalance results effectively by the different distances that you see between the coils. If you look between A and B and A and C, those distances are equal. But look between B and C, and they're different. And regardless of the layout, you can't make them equal. And so you don't have an ideal system. And as a result of that, what's historically plagued people is they haven't been able to get to the plot here on the right. The oscillations have been significant, not to the level of single phase, but significant that it wasn't particularly attractive. And so this technology is about how we developed, and this was a group, a team effort led by Aaron Brovant, Dionysius Elaprantis, myself, and students. And we've been looking at this and how to model the system and how to come up with a topology that makes things, you accept the imbalance, but you still get power oscillations that are small. And that's what we've done. The rest of the slides articulated that. I'll just show that we've done the testing in hardware of this. The patent technology is all about laying out the coils in particular arrangements to overcome that and create low power oscillation. So the key result is this. On the bottom left, it says output power out of our unit, and you can see it has very small ripple component. And that's what we were searching for, and that's what we've been going to do. We've done preliminary patent on it. We also have IP disclosures that are being generated on the practical instantiation in the roadway. You can do kind of some neat things with misalignment detection that we've also prepared disclosures for. And we're right now in the letting process of showing this and demonstrating on the order of, at the roadway, transmitter will be, I should say, at the vehicle, at the output of the receiver will be a peak power of 230 kilowatts. On average, at the vehicle will be on the order of 180 kilowatts. So that was a quick version of it. And I think we have a little bit of time for questions.
We do, Steve. If anyone has any questions, please feel free to ask or post in the chat.
So Steve, PT Jones, I'm from Oak Ridge, but I'm on a detail to the US DOE. Love to see the tri-phase or the three-phase on a dynamic in a different architecture than I've seen from our folks downstairs, I guess I'll say, with their polyphase. I noticed that it seemed like a fairly long loop, rough spacing on that length of that loop versus the cross-sectional.
The way that we're doing this is the length, we're kind of abiding by how you construct the roadway, which is usually in 15-foot segments in Indiana. So the coil length is 12 feet.
Awesome.
That accounts for, in essence, the dowel rods between those sections.
Mm-hmm.
The width on this is on the order of 3 feet, just over 3 feet.
Well, this is something that I've been trying to push, I won't say industry-wide, but researchy wise on the, everyone thinks that, and I also really appreciate the reference to heavy duty being a dominant player in showing the cost benefits of doing this. You can't just play on the light duty realm. But when you're looking at this from the standpoint of square footage, trucks have a little bit more square footage if you want to change the coil, receiving coil. It's still, even on a vehicle, a smaller light duty vehicle would still be able to work over the longer loop. But that was one thing that I really want to push and try and get the right folks with a little funding excited about doing some comparisons on those dynamic coil architectures or layouts. So this is really good work. Thank you for sharing. I look forward to the next presentation.
Thank you. We'll put more detail. I'll just give you a heads up that on a Cummins vehicle, we're doing this in tandem with Cummins in terms of demonstrating on the Indiana roadway.
Mm-hmm.
Their receivers on the order of 6 foot. We could have gone wider on the 3 foot, but for a host of reasons we didn't. But one of the advantages of this topology is you can just scale the power levels to the vehicles by the receiver length.
Mm-hmm.
So if you
Nice.
need 100 kilowatts, then you would effectively just say receiver is 6 foot. I'm 3 foot.
3 foot, right? Cut it in half.
And so it's compatible with that.
Okay, very good. Well, I am still doing a small, it's more literature research, but also documenting some of the other pilot programs in Europe and other places. So I'll definitely reach out to you with some of this. Looking forward to what you guys do in the future and your Indiana deployment. Thank you.
Thank you. Thanks for your time.
Thank you. Given the time, you feel free to also send us questions, but we'll probably have to wrap it up here. We'll look forward to having Steve back and probably give a more in-depth presentation, one of our future Tech Talks. I'd like to thank everyone for joining us today. Just reminding you that we are recording the session. It will be available eventually on our website. And I will be distributing a list of our technologies that we talked about, but any questions, please feel free to reach out. More than happy to help you. And thank you so much for everyone joining today. Thank you.